Welcome back, everybody. Sorry for the delay and sorry for the audio just a second ago. I got good news from Zoom. We won't be losing any videos anymore. We're allowed to render them on our own now. I don't think that affects you, but should create easier video uploads in the future. We had some requests offline, and I will be trying to get those going. It's going to be a little awkward here. Let's I have this document open and I'm trying to find it. Here we go. So we're going to do fall 19 questions 7 and 11 from page 1, which I have open over here. I will start sharing the screen and snipping and pasting. And it's going to take a second. Seven, 11. Aha. 7's a nice one. Need snipperdoodle wherever it is. There it is. Do an NMR problem. Need starboard. Wherever that is. Here we go. Okay. So let's try this problem here. Which compound below best matches the following spectrum? All molecules are C12H21ClO3.
Dr. Whitaker,
Yes.
can you share the screen with us?
Oh, I'm not even sharing the screen. Thank you for spotting that. Very awkward start this morning. Sorry. There we go. And here we go. And there. Which compound below? Nope. Let's get on the right program now. Where are you? Okay. Best matches the following spectrum. Where would I even start on this one? Well, it seems to me looking for unique things would help. We have an NMR table that says we shouldn't be looking for things here and here because every molecule has those. And I expect those to be here. I have a good question for you. Maybe it hasn't been discussed verbally, but right here, we have 4 H's that should be delta roughly 3.8. They're in this category here, are CH2OR prime. My question for you is, why are they a singlet in this right here? And some of you have read comments on exams and old lecture notes that says, if your neighbor is identical to you, then it's not your neighbor, it is you. Which means this CH2, sure, it has 2 neighbors, but there's no distinguishing this CH2 from this CH2. So they are not neighbors to each other, and 0 plus 1 gives a singlet. And we can't use this as a unique feature for the molecule because every molecule has this acetal protecting group. Similarly, every molecule has CH3 with no neighbors here. That's this CH3 here. And every molecule has CH3 with 1 neighbor here. That's this here, a doublet. So I'm going to zoom in on getting rid of options that don't fit. Every one of these molecules has alpha CH2 with two neighbors, CH2 with two neighbors. Ah, this one doesn't. That is a good place to start. This would be delta 2.4 roughly, and a triplet. Do we see that? Yes or no? And the answer is yes. So let's get rid of molecules that don't have that kind of delta right here. This H and this H, both 2.4, but singlets. We got rid of a molecule. And this has the 2.4 triplet. This would also be eliminated for the same reason as the one above it. So out of here. And this would be a 2.4 triplet here. So we're down to 4. Oh, and there's even a comment here I noticed. Vicinal hydrogens are not identical. That are identical twins are not neighbors. That's something you should know for your test. It's helpful. What about right here? Why don't we stick with A until we can eliminate A? What would this be? Should put it in green. That's an RCH2R. We'd expect that around 1.3. And we'd expect it to be a triplet in A. And we have that. Let's look at the 2 point. I just put a 2.4 check mark here. And triplet, 2.4 there. Similar story here. And did they all have that of the remaining ones? I could have saved them some time here. They all have that, don't they? So we still got 4 candidates. What about this guy here? Maybe we should go from here. That has 2 neighbors. That is just a little above 1 with 2 neighbors. So it could be 1.3 with 2. Oh, that's this one. Sorry. The green. And what about this guy? Well, they all seem to have that too. That's the R3CH. Put that in black. And it's got 6 neighbors. You know how I know it's got 6 neighbors? Because it's a heptet. And that's just all of these guys. And here we go. Are we going to eliminate any of these things? Is there anything we can use to eliminate these ones, or else we'd have to accept every single answer? What does this thing have? Yeah. What did the answer key say on this one? Anybody know that offhand? What's the answer key say about this one?
It's A.
It likes A. Is there any reason here that D can't be the answer? Because, you know, if I'm reevaluating this, I don't see a reason not to accept D. What is the difference between A and D? Absolutely nothing, because the molecule simply flipped. So I would accept D as well. It's the same molecule. Unless I'm misinterpreting it, it is the same molecule. So addendum eventually. A and D are the same. What about C? Looks like the carbonyl just moved. Is it flipped again? No. Different molecule, but I don't see a reason not to accept C either. So, and what about A and D, C, and what about A, B? Is there a difference? Is another flip scenario? It's another flip scenario. So it was a real easy question. Got 4 things that work. I will make sure yours doesn't have 4 things that work. And our next request from the same person. Where's my email? Here it is. Page 3, drawing bicyclo with a proper stereo center. Okay, that sounds like something we can do nicely here. So we're moving, getting our test. And we're looking for our test. Where are you, test? Here you are, page 3. Page 3. I think it was part 3. Sorry, I misinterpreted that. Part 3 is after that. Drawing bicyclo with proper stereo center. I assume we want to do that one. It's good review anyway, regardless. So we'll grab it. And here it is. And on your test, you won't have the boxes. You'll just have the words, and you will just draw the molecule. All right. So how do you do a bicyclo? We're pros by now, right? You draw your dots. We need 7 carbons between the dots, 7 extra carbons. 1, 2, 3, 4, 5, 6, 7. Doesn't have to be pretty, does it? And we need 3 between the dots. 1, 2, 3. And 2 between the dots. 1, 2. And we have stereo centers on 1 and 9 for sure. You're the boss. You decide maybe this is 1 and this is 9. And that would make this 8 and this 2. Biggest bridge first. And you're going to put benzyls on 3 and 9, but on 2 you have a double bond. 2 has a double bond. A benzyl on 3 and an aldehyde on 2. Do we want 2 to be E or Z? Well, that's handy. Here it is. Now, even if you drew the wrong kind of zigzag for 2 to 3, just make sure, even if it's not pretty, you draw the aldehyde and the benzyl group, because I'm pretty sure those are going to be on the high priority items on your double bond. And carbaldehyde on 2 looks like this. And those are Z. They are on the same side. And on 1, we have a terthexyl. So you draw your chicken foot. And you, okay, didn't like that. Draw your chicken foot. And you extend one of the feet by 2. Doesn't matter. It could be the middle one, end one. Just make sure you got 6 carbons when you're done. And terthexyl, sorry. 9 has a benzyl as well. You're not allowed short forms, so make sure you draw nomenclature. You always draw the phenyl group out in its fullest. So we got those 2. We got this one. We have the ene and we have the aldehyde. We are ready to think about stereo centers properly drawn. 1 needs to be S. In the current configuration, it's a tricky call for 1. Not impossible. There's a reason why I like this for 1 and this for 2. And here it is. Both carbons have nothing but bonds to carbon. And if you break it down, this is 3 bonds to carbon. I will count them. 1, 2, and the second bond is a third bond to carbon. 1, 2, 3. So it's a tie. Now go to the carbon attached to this that will have a highest priority, C with an O. Any of these C's have as high a priority as that C with the O? And the answer is no. That's why I went 1 and 2. I like group 3 to be the one that hits a branch early, and 4 hits a branch later. You only use the hits a branch statement when it's nothing but just CHs and no pi's, nothing fancy. Connecting 1 to 2 to 3 right now is a clockwise direction. 1, 2, 3. We need it to be counterclockwise, so we put the 4 on a wedge. Remember, that's the equivalent of a single switch. Just make sure the dash is adjacent to that and be done with it. Make sure the dash goes all the way and the wedge goes all the way to the bond, at the end of the bond. On 9, we need an R stereo center, and a CH2 that goes to a C with nothing but C's is number 1. And a CH2 that goes to a branch earlier beats a CH2 that goes to a branch later, beats a CH2 that goes to a branch much later. And 1, 2, 3 is currently R, needs to be R, put the 4 on a dash, be done with it. And I think that gets us full credit on that. 4 points, not to be sneezed at. And saving. Sorry, I haven't saved yet. Usually I have that done ahead of time. Things are very interesting right now. We'll settle down later this week, I promise. 242. And there you go. Okay. Next request was for, I'm looking for my next request, was for part 4, the acid base problem, which is one of the early problems. Good choice. And moving on over to the test again. And right here, right, that's good. We can do both. On your test, there'll be one, but hey, could be either one, could be a new one. Let's just grab the whole thing and move on from there. It'll look like this without boxes. And snipping. Snipper, where'd you go, Snipper? Didn't click on the snipper. There you are. And I don't have the right thing open now because I clicked on the wrong thing. It's a comedy of errors here. Now I need the snipper. Okay, gotta grab everything. And moving on over here. Once again, all of this is fall 19. I didn't put that label on the previous page. I will now. So we're supposed to fill in the missing pieces. We got a major product from an acid-base reaction, and you know it's an acid-base problem. It's all about pKa's and pKeqs. So you're taking a proton off with a base. The base, ethyl minus, becomes ethane with a pKa 50. The H's that are options are this one or this one. The question is, which one will be a better anion? And the answer lies in the resonance form that has a double bond going here versus there, which is more substituted. But the original product that I like for my major will be this one, the H missing there, and the minor the H missing there. Resonance forms, and yes, sulfur can handle this. I like that resonance form better without the charges. I like this one of the two the best because it's got more hyperconjugation on the pi bond. So we've got that going on. And we have to know the pKa of a ylide precursor, regardless of whether it's a sulfur ylide precursor or a phosphorus ylide precursor. You will have a pKa 30. I can almost guarantee it on this question, because we saw at least 2 of them, maybe 3.
Doctor,
Yes.
can we please just like review all the new pKas that we had in the course?
Sure, we'll do new pKas under here when we're done.
Thank you.
And don't let me move on to the next page, because you know I got it out of mind right now because it's out of sight. And after I'm finished this, remind me. Oh, don't forget that new pKa, unless I remember. That could happen too. pKa, fill in the missing piece, did it. Draw a more stable resonance form, did it. You don't have to show the arrows, and I won't make you show the arrows. Place pKa's onto the acids, did it. pKeq coming up. Left acid minus right acid, always. And I always make you calculate KEQ. 10 to the positive 20. Big time favoring products. And on your test, I will try to remember to break this down into 2 more easily circlable. Oh, wait a minute. You're not circling anything. You will be drawing the more stable favored arrow. Circle the favored arrow. Just draw it. Say right side or left side. And that's not too bad, is it? And then the next one, carrying on, we've got alpha H's to a ketone is the best, and that's a new pKa as well. Both of those are going on our list. 20. And for a HOAC, I'd like to remind you what there's HO, and here's what AC looks like. Carbonyl CH3. That's a pKa of 5 because it's a carboxylic acid. pKeq, 20 minus 5. This reaction is not going to go to completion, is it, at all? Positive 15. KEQ, 10 to the negative 15. And I want you to draw me the cyclodecanone enolate. Oh, not the most stable form. Draw the one where the minus is on the C. And then its resonance form. Oh, major and minor. You know, I know what happened on this question. I meant to put a methyl on one of the alpha positions, didn't I? Right now, it doesn't matter which H you take, does it? So, in this, there's no need for a minor because they would have exactly the same stability. Just knowing how my mind works, my reason for having that minor was in my mind, I probably had a methyl alpha, and you pick the double bond where the methyl was over the double bond where the methyl wasn't. Didn't happen here. And we're going to circle the arrow to the left because the acid on the left is more stable than the acid on the right. 20 is more stable than 5. This one we circled the right because the acid on the right is more stable than the one on the left. And I think we have a question.
Yes, so we did the double bond on the between the O and the C.
Between the C with the O and the alpha position, yes.
So not between the other 2 carbons that
No,
adjacent to
that would be an octet violation if you tried there.
Okay.
So you got a lone pair on the C with a minus, and it resonates in to become an O minus. And our new pKa's were alpha to carbonyl. Now I have to be more specific because later on we're going to see other carbonyls have different pKa's, like esters are different. Right now you're only responsible for aldehydes and ketones, and the pKa is 20. So if you want a short form for that's the one right there. And off the carbonyl. And then we had ylid precursors. So either a phosphorus ylid, in which case we had 3 phenols, or a sulfur ylid. Most often phenols because you need a group that doesn't have H's on that carbon. And both were pKa 30. And we had the Arbuzov reagent. And it was a phosphite ester. RO, two of those, double bond. And the pKa was 20 again. 220s, 230s. That helps, right? And we had another 30. Let's make it a third 30. I'll put it up here with this one. How wide are we here? Yeah, we got a little room. Maybe I can move this. I don't know, put it up here. Put a line here. And we had the dithiane, also known as a sulfur acetal. And it looked like this. The R groups could be connected. They don't have to be. And it was also a 30. And I think that covers all the new ones for this chapter, for this test. And that was good review. And then the next item on our list we had, let's see, part 4, 3F, a mechanism. Finally, haven't done a mechanism in, seems like forever. So excited I dropped my pen. And it's coming up. We've got here, and we've got this. No, gotta get there first. 3F. That'll be quite a ways down, I think. There it is. Oh yeah, it's a nice one. It's got some old mixed in with some new. And we need, here it comes. Still fall 19. And we have an acetylide ion here. Need a lone pair on there somewhere. I'm going to just draw out this acetylide ion. There. And clearly it's attacking the most substituted, least substituted carbon. It ended up here. So this part, straightforward, attack and make O minus. You can't combine these steps because they're numbered. And we have a phenyl attached to a C that's got a dimethyl next door and an O minus. And now we've got an acetylide species there. And HCl will get us up here. And there you have it. And this one you're saying, oh, I don't know. I've never seen this reaction before. Please don't panic when that happens. It's going to happen. This is the evolution of teaching students organic chemistry to see if they can apply previous knowledge to unseen things. We clearly are making a bond from O here. This is the same O. This is the same O to the carbon here for the first product, and we'll have a double bond remaining, or the O here to make this product. In either case, we have an alkene, which means in this example, we put a proton. Yes, sulfuric acid has a proton. A proton ended up on the CH2 where there was only a CH before. Where does it get the proton? It got it from the strong acid. So we're going to make a major and a minor carbocation here. Yes, they don't go away, do they? So we've got phenyl, goes to a C, goes to a C. That phenyl doesn't look so good, does it? Looks worse. Phenyl, C, goes to a C that's double bond, and the cation could be here. Anticipating that H disappearing later. And you're also going to make, if you put the the H on the internal position, then your cation, let's see, 1, 2, 3, right? 1, 2, 3. Here, and I'll show the new H's just in case you're wondering where the new H is. And the new H one here and the other one. And we've got the same OH situation here. And the first step would definitely be lone pair attacking the cation to make the OC bond. And the second step, any color other than red, would be the base, which is sulfate ion, hydrogen sulfate ion. You made one when you made the first cation. You made one when you made the second cation. And they can now be used to regenerate the catalyst and deprotonate to give the final products. Evaluating carbocations means this one with more hyperconjugation is made in a higher amount, means the product that it gives will also be made in higher amounts. And I hope you like that mechanism. It's a nice little start. And then we're moving on to winter 19. Although this would be a nice little break, wouldn't it? We can come back at 9 o'clock. And we're going to start off with winter 19, I think multiple choice, 13, 14, 15, 16. And I will see you very soon.